So I'm really excited that Adeline is presenting again. Adeline has been one of the maybe longest sort of coming to every haystack. I really appreciate it. And so really excited about this talk. You know, we're used to large numbers these days in a way that we weren't before, right? A million? Yeah, okay, it's a million. But I think billion, B as in billion, is still a big jump. And so I'm really interested in finding out what they have been doing. So I'm going to hand it over to Amine and Roudy for their talk, and looking forward to it. So.
Thank you, Eric, and welcome everyone, and thank you for joining this session. I am Amine Gani, and with my colleague Roudy, we will talk together about semantic search at scale. We see a lot of fantastic demos about semantic search, but it work only on a small data set. But we thought that we wanted to see what it will be on a large data set. For example, if we have billion vectors in production, how it will work. So before we will just introduce ourselves very rapidly. We are both software engineers. We work at Adeline. It's a company specialized in search engines and also in data. We work mostly on Elasticsearch and OpenSearch, but we also work on Solar, for example, or Lucene. We do multiple services, basically consulting, some trainings also, and we do also software developments based on this technology, for example, Elasticsearch or OpenSearch.
I'm going to barge in for a moment. You guys are working on the audio, right? Working on it. Excellent. So this is the first talk in here, right? So they both get the honor of being the first one and also get to debug the last bits of the audio with everybody in there. So bear with us, and if you need to go 5 more minutes or whatever, we can do that.
Thank you. Du coup, attends. Okay, go. Okay. So, ça marche plus. Ouais. Stop. So before diving in our subjects, we will talk a little bit about lexical search and semantic search in order to understand why this complexity exists and why we need this solution in the first place. So lexical search, I think everybody here knows what is it. So it's the traditional keyword search that we have for a long time and we use. So it's match the exact words or phrases that we have in our query with our documents. So it is based on inverted index. It uses tokenized text. The advantage of lexical search is that it is fast and it is low on cost and in terms of resource. But the problem is that it misses context and intent of the query, so we need a lot of configurations, and to maintain it, for example, adding a lot of synonyms, dictionaries of data, some stemmings and lemmatization also. And with the LLMs these days, the query language become more and more natural, so lexical systems doesn't understand the meanings behind these queries, and we need semantic search approach. So what is semantic search? Semantic search is a shift from the literal text matching. It goes deeper in understanding the meaning and the intent of the text that we have, and it's based on transformers, and we convert the documents that we have into embeddings, into vectors, so it's numeric representations in multi-dimensions principally, and each vectors will capture the context and the meanings of the words that are, or maybe the images or the audio, so the meaning of the input that we have, and allow us to compare it semantically with other items that we have. So the big advantage of this is that we can do the same on the query side, and we will search for the similarities between the query and our index, and we will have a better relevancy. So especially for natural language queries, so even if our words doesn't exist in the items that we have in our index, but they exist in the document query, we will still have matching between these two, the query and the items. But the problem is that it's much heavier in terms of resource, so we need more RAM, more CPU or GPU and disk, for example, and we need specialized infrastructure. For example, some graphs our quantization that we will see later in this talk. And since we talked about lexical query and about semantic search, we will talk also about hybrid search. So it's an approach that can mix multiple types of search. It can be multiple types of query, lexical search, or in a lot of projects that we saw, it's principally lexical search and vector search. And in order to have fast results and have, we'll say, improved relevancy, we will use a first phase that will get the top candidate documents using sparse search or lexical search, for example, with BM25 to get the top 100 documents for our search. And then we will compute the similarity with the dense vectors, so the semantic search, to re-rank these results. So the advantage here is that we will have better relevance, and it's not very cost effective in productions. But when we are here today to talk about the semantic search, so we took an example for Elasticsearch. How does it work in practice? So we can it can be very straightforward, for example, to use the semantic text type in Elasticsearch. It is recommended by Elastic documentation. So we will need to create an inference API. We will need to have a model to create our embedding, and we will need to define our index mapping. So we will use this type, the type of semantic search, and we will use the semantic query to search our documents. But we can do it also in a more complex way, we can say. So we can have our own models that we can deploy locally on Elasticsearch, or we can also have externally deployed models, for example, from Hugging Face, or it can be also from another cloud provider if we want to just externalize these parts to generate our embedding. But if we deploy it locally, we should pay attention to have a model that is compatible with Elasticsearch or OpenSearch, for example. But we always need this model to generate our embedding. And we also need to define an index mapping with the correct type that we will use and who will work better for our case. And the same for the search parts also. For simplicity, we will only focus on dense vector in these presentations, since they represent the semantic representation that is richest in comparison with the sparse vectors. So we need more computation. So it have a higher cost. So we will only talk on dense vectors. We will take an example to see how dense vectors works. By example, in this example, I choose to vectorize to create an embedding of a cat. So I choose to embed it based on 3 dimensions. So the size, the kindness, and the intelligence of the cat. So I choose also to have vectors with numeric values between 0 and 1. So the cat is not a very big animal. So we will have 0.25. And it is very friendly and intelligent. But we will also vectorize another type of animals. So for example, dogs, elephants. And we see that we have these animals in a sort of clusters of the words. And we see that the dog and the cat are very similar, but not the elephant because it's bigger. But this not means that it will be the same for all the models. It's just because we choose our dimensions, which are the size, friendliness, and intelligence. And often we see some presentations of semantic search only with 3 or 4 dimensions. So it has we can say wow effects to say it works very well, but in general we have much more than 3 dimensions. For example, this little board of models from Hugging Face. In general, we have dimensions when, for example, thousands or hundreds of dimensions. So we have a lot more data, and we should store also all these vectors and do some search on them.
Okay, semantic search is often hailed as a game changer in the world of solving challenges like complex sentence analysis and synonym detection. So we can do this with just a few embeddings and a machine learning model. However, what happens if our vector reach a billion level scale? So how can we handle these billion vectors? So in this presentation, we will go past the hype of semantic search, and we will explore the complexities that comes with managing large-scale vector databases. So here in this presentation, we will focus mainly on Elasticsearch and OpenSearch. And while building our vectors, we might be splitting our documents into chunks before embedding. Also, we might be vectorizing multiple fields in the same document. And we could be also using multiple models in order to support different languages or different tasks. So all of this adds up so fast, and we can reach a billion vector very fast. So that's where things gets a bit tricky, and that's what we will see next. Okay, so let's talk about how we actually store these vectors in Elasticsearch. First, we need to define the type of vector, which is the element type. The element type is defined at index creation time, so it's in the index mapping. And this choice has a huge impact on storage and on memory usage. And the available options are float, byte, and bit. The float has higher precision but uses more space. And so if we can tolerate a bit less precision, we can use the byte, and this way we save up so much space. And lastly, if we want to really go minimalistic, we could use a bit, but this is less commonly used as it requires specific setups. And here for this parameter, the default value is float. Now let's switch to index options type. This parameter tells Elasticsearch which algorithm to use for indexing and also for search. So some of the available options are HNSW and flat. HNSW, which is a hierarchical navigable small word, is the most commonly used. It's a type of approximate nearest neighbor ANN algorithm. And the flat, it uses a brute force KNN algorithm to search over all our vectors in our index. So it's a brute force technique. So we can observe here that it's not scalable at billion vector level, unless you're okay with the high latency and lots of compute. Now let's get into the details of each type. So flat indexing, it's the simplest form of indexing. As we said, it uses a brute force method. So all our vectors are scanned for similarity. So here in this example, let's imagine our vectors as node in this cluster, and we have a query. In order to find the nearest neighbor, we have to compute the distance between our query and each of the nodes that we have in our cluster. So the time complexity of this operation is O of n. So we can say that it does not scale well with very large data sets, which is why ANN methods like HNSW are often preferred for large data sets and for production. In order to understand how HNSW works, we will go over two concepts, NSW and skip list. First, NSW, which is navigable small word. The graph looks a bit like this. We can imagine that each vector is a node in this graph, and each node is connected to other nodes based on how much they are close in this vector space, and also connected to a few nodes which are a bit farther than the closest nodes, and this is in order to reach far areas in this graph, on the graph. So in order to navigate this graph, let's take an example. We have our query in orange in the middle. we will take a starting point. Let's begin at 2. No, this works. Yeah. So 2 is connected to 1 and 6. So we'll calculate the distance between 1, 6, 2 and the query. Each one was the query. So here we can say that 6 is closest to the query. So we switch to node 6. Then we do the same. Here 6 is connected to 2, 3, and 8, and 5. So we calculate each distance. We find that 5 is the closest to the query. So we switch again to 5. Then 5 is connected to 6 and 4. So we calculate the distance again for this 3 node, and we find that 5 is still the closest to the query. So we choose 5 as the closest, as the nearest neighbor to the query. However, there is one limitation to this to NSW. Let's say we begin by the node 7 as an entry point. Here we calculate the connected node to 7 are 1 and 8. So if we want to calculate the distance with the query, we find that the entry point is the closest to the query. So we stop here. So, and this is called the early stopping. So here we missed all these nodes that are closest to our queries and this one. And in order to overcome this limitation, here comes the HNSW that we will cover in the next couple of slides. Before that, we need to define our skip list. A skip list is basically a data structure that allows fast search, insertion, and deletion. It's like a balanced tree based on linked list. It uses multiple levels of linked list to skip over elements in order to speed up operations. So our skip list looks like this. The bottom layer, level 1, is a normal sorted linked list. Here we have A, B, C, D, E, F, G. Then when we go higher, on each higher level, we skip some elements. So here on level 2 we have A, C, G. And on the top level, level 3, we have very few nodes, and we have not just enough to make a fast jump between element and another. And in order to navigate this skip list, we start at the top left. Then we can compute here the similarities, and we go down a further level until we reach our element. So here we can see that we did not evaluate all the elements in this list. So the time complexity here is O log of n, which is less than O of n with k and n. So let's see how we can build this skip list. Let's say we have a skip list with some elements already inside, and we need to add new elements. So, okay, let's not look at the GIF because it started before, I think. But how, as we said, we should start with the top left element. And here we need, for example, to insert element 80. So we start by comparing 80 with each of with the top left. And if we don't find the place for 80, so a number bigger than 80, we go down the levels. So here is 80, we compare to 30, 80 is less than 30, false. We go down level, we compare with 50, it's not less. We go down a level, we compare again with 70, it's not less. We go down a level, we compare with 90, so it's less. We inserted between 70 and 90. Then after that we flip a coin. If we get head, we go higher one level and we insert our 80, then we flip again. If we got tail, we stop, and we have our element in this list. Now for another example, quick example, 45. Here 45 is less than 50 on all of this, so we go down to the deepest level and insert 45 between 40 and 50. Okay, so if we merge these two concepts together, the skip list and the NSW, we obtain the hierarchical navigable small word. So the graph looks a bit like this. It's basically a linked list on top of each other on each layer. So for example, if we have an entry point here, we calculate the adjacent distances and we go deep down the layer until we find the nearest neighbor to our query vector. And here we can say that we did not evaluate every node, so ANN is faster, but it's less accurate than KNN. And here we have a few parameters, key parameters that we should take into account, M and EF construction. So M, it's the number of connection between each node and the graph at a given layer, and EF construction is the size of the candidate list during graph construction. So for these two parameters, the higher the level, the more accurate, but it becomes slower and more memory usage. So we should find the middle point in between, depending on our application. Okay, so in all of these algorithms, we talked about measuring distances, and we have multiple ways in order to do so. So here we present three ways, which is cosine similarity, Euclidean distance, and dot product. First, cosine similarity is most commonly used and is preferred for semantic text search. Euclidean distance is more common in feature-rich vectors like images. And dot product is generally used when our vectors are not normalized and we want to take into account the length and the magnitude of each vector. So if we get over quickly each distance formula. So for Euclidean distance, if we have two vector of 2D dimension A and B, the distance is the square root x1 minus x2 minus x1 squared plus y2 minus 1 squared. And if we have multiple dimension, it's the sum of I going from 1 to n of the same formula squared. So this is Euclidean. Cosine similarity. Here we are actually evaluating the angle between our vectors, and we do it with this formula. It's the dot product of A and B over norm of A times norm of B. So here we can observe that the narrower the angle, the more similar are our vectors. And when our angle become too broad, we can say that our vectors are opposite. So we'll go over quickly the use cases of each. So as we said, the cosine similarity is usually used for search engine and NLP embeddings, and Euclidean distance for images and other feature-rich data set. And for mixed or hybrid models, sometimes we can use a combination of both. And finally, if we don't know which one to use, we normalize and we try both.
So now that we saw some types of, in the index mapping, some search techniques, when we have a project of semantic search and we arrive with a huge dimensions and we need a lot of RAM, for example, the DevOps team or the architects are not very happy. So there are some techniques to reduce the cost or the memory needed to have our vectors. So we will talk about quantizations. Basically, it's all about reducing the size of vectors so we can store them in less memory and we can search faster on them. So we have three main types for quantizations. We have the first one, it's the binary quantization. So it will just reduce our vectors to a vector with just 1 and 0 values. So it's binary. It's very straightforward. It will consume less of memory, but we will lose a lot of accuracy. And we also have the scalar quantizations. We saw that the default type is float, so we can just map this float onto an integer, and we will have a smaller vector, but we keep more accuracy in comparison with the binary quantizations. And we have also the product quantizations, so it will split the vector into smaller subvectors and quantize each one. So we will have chunks of vectors and it will be quantized. This can compress much more than the other ones, but it's a little bit more complex, so but it gives the best compression to accuracy trade-off. And why we do this in general, it's because we need a lot of RAM, and we cannot host large vectors and have good performance for search and relevance in general when we have the trade-off of speed, search speed, precision, recalls, and memory and disk usage. So we need to find what is the best for us for our use case. If we can do, for example, brute force, because we need very accurate results, but the time is not important. And for example, in e-commerce, the time is very important, and we need also precision. So we should do some benchmarking and see what it's the best for us. So a little example of the needs of memory requirement to have in our Elasticsearch or OpenSearch to host our vectors. So in our case, we said that we want billion vectors. We will take a vector of a dimension of 1024. So in general, we need the number of vectors, the vector size, and the vector type. It's a float, and a little bit overhead of the HNSW method that we will use in our case. So we'll need a little bit less than 4 terabytes of RAM. So when we say that we need this amount of RAM, it can quickly stop the project. So it's a no-go unless we are in a very big company that have a lot of money and also have a solution that we can be sure that it will give us back this money. So we will use, for example, in our case, the quantizations with int8 instead of float. So we will reduce memory, and we see very fast that required memory is much lower than the first case. So we basically split it by 4, and we can also split it much more with other quantization type. So they are very happy when we come with a solution like this. And we can see that we can also reduce more with other quantization technique. So we just put here a slide with different types of quantizations, basically with mapping in other types. So int8 in our case for our demo, and int4 BBQ that is recently released by Elasticsearch. Not very recent, it's been some months now, but we can really improve this memory needs. So there is just a slide for some quantization methods that we have in Elasticsearch, and a description if they are very accurate, not accurate, if they reduce, if it's very fast for the search. We don't need a lot of memory, but we lose a lot of accuracy, and etc. And we have also the same in OpenSearch. So we can basically do it natively in Elasticsearch or OpenSearch, but we can also do it externally if we want to not have this overhead in our search engine, for example. So to have 1 billion vector at productions, in general, we won't talk about one single instance at this time, because we are in productions, we have a lot of data. So in general, a standard configuration for Elasticsearch or OpenSearch, we have nodes of 64 gigabytes of RAM. We allow the half of it for the GVM, so garbage collectors and other stuff, and the remaining gigabytes of RAM are used by the file system cache. So in this case, we will decide to store the vectors of heap. So we will use the file system cache, but it can be very bad for our operating system. So we can have very bad performance. So we should do some benchmarking with this configuration to see if it works or not. And basically, we won't just store the vectors in our Elasticsearch in the rest of the RAM, and we will say, okay, it will work, because in our cluster, we also support another type of search. We have metadata of the cluster, for example, and at this scale, we don't have one single instance. For example, for 10 gigabytes of vectors, we won't have a single node. We will, for example, have 20 data nodes approximately. So we also need coordinating node. Maybe we also need dedicated master node at this scale. That is obligatory. And we also maybe do our ingestion and computing in our machine learning nodes. So logically, we will need maybe more memory than we expected.
So we saw a couple of configuration at index level in the mapping and the setting of indexes. However, there are still one or two parameters that we can play with. In fact, we can add a parameter in order to tell Elasticsearch to load our vector files into the cache directly on cold start. So this setting, index store preload, it will directly load our vector files instead of waiting for Elasticsearch to lazily load the cache at each query. So it's very useful for reducing cold start query time, and we can use which vectors we want to load in the cache based on the extension. So if we have vex for HNSW graphs, VEQ for quantized vector, and VEC for all non-quantized vectors. However, be careful on using this because preloading too much can backfire. Because if we overuse it, it might actually slow down the search performance due to memory pressure. So we should use it strategically, and we should only use it on indices which are the most important or which you want to query the most. Here we went over how we calculate the disk memory required. However, one point of attention here is when using Lucene quantization, both quantized and non-quantized vectors are stored within the KNN vector field. And if you need to analyze the disk usage, we can run this command, our index / disk usage, in order to see how it's being used. And in addition to that, non-quantized vectors are stored twice, once in the KNN vector field and once in the source field, so underscore source. And we can disable that by adding this in the mapping, so source exclude, and we give it the name of vector fields. However, if we did this in order to save space, we lose the functionality to reindex, because if we reindex, we lose our data. So it's actually a trade-off between operational flexibility and storage optimization. Here we did a comparison between once with storing vectors in source and once without storing it. And we did it for multiple element types, for example, float, int8, int4, and BBQ. And here we can see that we save almost half disk space by disabling the storage of vector and source. And we can reduce it even more. So in order to maximize memory savings, we should do a quantization. Either we do external quantization with an external program like in Python that creates this embedding, quantize it, and send it to Elasticsearch, or we create directly a pipeline in Elasticsearch in order to quantize our vectors. So we prepared just a quick demo in order to show the difference, the impact of element type on disk space usage. So I'll switch. Okay, I'll clean all the index. Okay, so here I have a Elasticsearch 8.17, I think, with a single node. We'll start first by creating four indexes with their mapping. The first one would be the demo float. So here we used element type float. We'll go ahead and create this. The second one, this will be used for byte. And here I put the number of replicas 0 because I have a single node, and I did this to preload the cache. And here the rest of the mapping for the vec field. I did this, yes. Then the third one will be for BBQ. It's also on byte, and the last one's for product quantization. It's also type byte. And so okay, so here in parallel, we prepared a couple of scripts. It's basically just a function that do BBQ quantization. So it performs k-mean clustering for BBQ quantizations, and converts cluster centers to binary codes. And another script for product quantization also uses k-mean, and the last script, it will generate float and byte quantization. So here we use this model for the embeddings, and we quantize after. And if we go ahead and run this script, okay, so I create 4 windows. Okay. Switch to my directory. Okay, so I will go ahead and run the first one, BBQ quantization. Then the second one, PQ quantization, product quantization. And the third one, it will generate 2 files, float byte.py. So here wait just a couple of seconds. It will generate, here it already finished, so it generated the BBQ quantization file, JSON file. Here is for PQ, and here it generates 2 files, float and byte. So if you want to look at the files, it's here. Okay, for example, for the byte one, it's actually a bulk insert for Elasticsearch. We give it the index and the vectors here and the ID of each document, and the same for the 3 other files. So now, given that we already created the mapping of the indexes, we can go ahead and do bulk inserts for this file. And to do that, we have a small script here that will take each JSON file and use the bulk API to insert them. And if we run this, okay, it already finished indexing our data. So if we switch back to Kibana, and we do a cat indices to view our indexes, and here I will add a sort by store size. Here the store and primary store size are the same because I have no replicas. So here, if we sorted by size descending, we can see that the float one has the biggest size. Then the byte one is almost 5 or 6 times smaller. Then for BBQ, it's like 10 to 15 times smaller than float, and lastly for PQ, it's 100 times smaller. So depending on our application, on our need, we can use some of these quantization method, and we have here the difference between the difference between the disk usage of these indexes. And now we'll switch to the conclusion with Amine.
So as a wrap up for this talk, what we have seen, we saw that what is lexical search, what is semantic search, we saw the difference between them and why we need all this complexity, because lexical search doesn't cover the intent and the context of queries. We saw how semantic search handled it. We saw that beyond the demo that we see a lot, it is more complex in reality to do it in production at high scale, for example, for billion vectors. But we explored this and we saw several strategies to do it at this scale, for example, with quantizations, maybe with some chunking strategies, keeping the source or not in the index. So it's generally benchmarking and trade-offs between what you need, what you don't need, and if you need precision, so you need more memory, you need to store bigger vectors. If it's not a problem and you don't need precisions, you can reduce the costs and have a little bit precisions. We should just note that sometimes we don't, even when we reduce the size of the vectors, we don't see a loss in the precision and relevance. Why? Because we are in a semantic similarity, it's not an exact match. So sometimes we should just test and see how it works better. And what's next for us, we will see after indexing these vectors, after storing them, to do some benchmarking with the queries and see how the clusters are with the high load of queries and indexation at the same time. Just to note, we have inference APIs for embeddings, so just a little advice, you should use two different inference APIs so that the queries does not impact, for example, the indexation. And we will continue to learn how we optimize our semantic search at this scale. And thank you very much for assisting to this talk, and feel free if you have some questions.
We have a couple of questions online that I'm going to grab and post into Slack so you guys can answer them. Do we have any questions in here? And I don't think I have the microphone. So, Gurian, speak up loudly.
I got it. So you mentioned briefly that you do quantization outside of the cluster. So I know OpenSearch has like quantization for ingestion time. Is there a reason you do bulk processing or like during ingestion time outside of OpenSearch rather than integrated within it?
In general, it's a trade-off. If you have, for example, machine learning nodes, or if you have memory and you can do it, you can do it in Elastic or OpenSearch. But if you externalize it, you can also test it offline. You don't need to test it in Elasticsearch directly, and it's more manageable. So it depends on your need. If you have memory and hardware requirement, you can do it in Elasticsearch, but it's better to manage it separately.
Right there.
Hey, given how memory intensive vectors can be, I found that we tend to remove replicas like you did in your example, but then we start to lose the high availability advantages that Elastic and OpenSearch give us. Where do you think that comes into the trade-off in terms of once you add a replica, you've got to double the amount of memory that you needed as well? Is it better to quantize down to the smallest amount to give you enough memory to then duplicate within the cluster to ensure that you can keep all sides of the equation?
It's very important to have replicas, so I will say yes. At this scale, we need to replicate our data. But yes, if you don't have enough memory, you should quantize and reduce the size of memory that you need for your vectors so you can replicate them. And it can also help for the search part. So when you have replicas, you can also parallelize your search requests.
All right. Terrific. I think that gets us to time. One more.
I don't have a question. I just wanted to say you had a slide that allowed
Okay, well, great. Thank you.
Great.